Welcome to this lecture on the topic of rule-based expert systems. During this lecture, we'll start by providing an introduction to rule-based expert systems. Then we'll take a closer look at essential components of a rule-based expert system, starting with the knowledge base, then followed by an examination of the inference engine, with a particular focus on the difference between forward and backwards chaining. And lastly, we'll briefly review other components of a rule-based expert system. Let's start with a brief introduction to rule-based expert systems. Recall our previous discussion of rules as a form of knowledge representation, where they typically take a simple if condition, then conclusion form. Also recall that we had previously provided a high-level review of all the typical components of an expert system in general, as summarized by this schematic. Rules as a knowledge representation are most commonly used in expert systems. In particular, rules of the if-then form. In such systems, rule antecedents are only permitted to be conjunctions, or ands. The inference engine in rule-based expert systems determines the rules that have antecedents which have been satisfied. Specifically, all conditions of a given antecedent must match facts in the knowledge base. If so, and assuming we're doing forwards chaining, this results in the consequent of a rule being activated or fired. We'll get into the specifics of forward chaining later in this lecture. Notably, an activated rule may subsequently generate new facts, which are added to the temporary knowledge base of the expert system. And this activation of a rule may subsequently lead to the activation of other rules downstream, when their antecedents become satisfied. So when are rule-based expert systems preferred? Well, first off, when knowledge is diffuse, in other words, when there are a large number of facts which are more or less independent from one another. They're also preferred when knowledge can easily be separated from its use. In other words, there's no dependency on how to use knowledge. For example, it could be used to decide the ingredients of an item, but it might struggle to handle deciding how much of each ingredient we need to mix up together for a tasty recipe. Another term you'll hear that's also useful to define is that of production systems. The term production system comes largely from industry. Here, the consequence of rules are usually actions. The term production systems is typically associated with the monitoring or controlling of tasks. However, there seems to be some inconsistent use of this terminology based on geography. On the East Coast, production systems usually refers to rule-based expert systems that use forward chaining in particular. But on the West Coast, the term production systems can refer to any kind of rule-based expert system. We'll assume that production systems refer to rule-based expert systems that utilize forward chaining. Here's a table briefly highlighting the difference between general rules used in artificial intelligence, for example the ones that could be extracted from decision trees, and the type we find in production systems, known as production rules. General rules, as we've seen, follow an if-then structure and are often part of a fixed hierarchical path. They also typically are executed following a linear or tree-based sequence to reach a specific classification or diagnosis, and they often rely on declarative knowledge representing static facts or a fixed decision path. Alternatively, production rules generally take the form of if condition, then action, and when fired, can modify the system's current state or memory. Execution of such rules is managed by an inference engine that matches rules against a working memory and resolves conflicts if multiple rules apply. And these systems generally rely on procedural knowledge that allows us to represent how to perform a task or change a state. Now let's move on to focusing on the knowledge base. Let's start our discussion of the knowledge base by first identifying the difference between a problem domain and a knowledge domain. Typically, an expert's knowledge is specific to one problem domain, for example, medicine, finance, science, or engineering. The expert's knowledge about solving specific problems is called the knowledge domain. The larger problem domain is always a superset of the knowledge domain that includes all knowledge about a particular domain of interest or focus. Going back to our schematic, we can see the knowledge base of our rule-based expert system given as the purple box and indicated by the green arrow. The knowledge base itself holds the expertise that the system can deploy. The knowledge base can be referred to as production memory when it comes to production systems. A knowledge base is usually developed for a specific expert task, and this knowledge base exists independently from the rest of the expert system shell. You can think of the knowledge base as including both the long and short-term memory of the expert system, where the long-term memory generally includes facts, data, and rules that don't change through the course of running the expert system, and the short-term memory can be thought of as the working memory. This would include case-specific facts that are added to the knowledge base either by a user or by the inference engine in response to a query being made. Now let's go through and summarize the major parts of the knowledge base, as they exist in many rule-based expert systems. On the illustration on the right, all the items representing long-term memory are given as blue boxes, such as rules, general facts, and questions to ask. And then our short-term memory is given by the pink box, which includes the case-specific facts. The rule-based part of the knowledge base includes implication rules that capture domain knowledge. The fact base of the knowledge base includes general facts that do not change. The fact base could also reference a database of key information or variable values. And then there's the question-based part of the knowledge base. These are questions generally written in natural language. These questions can request case-specific facts from the user. Then the inference engine utilizes the question's answers to determine if a given rule is going to activate. And then again in pink, there's the case-specific facts in the knowledge base. These are facts provided by the user for a given query. They can either be given as question responses when fewer facts are needed, or all these facts can be loaded in bulk when there are many unique facts needed or available to solve a specific problem. Diving into the rule base a little bit more, it's typically a largely unordered set of non-repeating rules. Depending on the task complexity, a rule base for real-world problems may contain a few hundred to thousands of rules. Assuming we're using just if, and then rules, how would rules generally implement a situation that required or scenarios? For example, if we want to say that if A or B or C, then D. Well, in the context of standard rule-based expert systems, we would just break this expression into individual rules. In other words, if A then D, if B then D, and if C then D. Also, here's an example of what a rule's syntax might look like in an expert system rule base. It looks similar to what we'd see used in first-order or predicate logic. The if part of a rule checks the condition of whether a given son is the son of a given father. The then part of the rule then determines that the given father is also the father of the given son. Now let's look more closely at the fact base. This tends to be an unordered set of facts that give values for propositions or predicate statements. Facts should follow the syntax of rules so that the inference engine can match facts to be applied to the appropriate rules. Going back to our previous example rules, here are some facts that we might have in our fact base. Notice that son of, with 2 entries, corresponds to the syntax of the if part of this rule. So these facts say that Steve is the son of Joe, and Bill is the son of Dave. And now let's look more closely at the question base. This is an unordered set of questions applied by the expert system in order to give the system a more human feel for user interaction. Typically, questions return the following user-entered values, such as yes or no, true or false, multiple choice, where the user has to pick one or all that apply, or enter a value, and that value could be an integer, float, or text. Here's an example of what a question might look like in an expert system. In red, we have the syntax giving the function whofather with variable answer. And in green is the text that a user would see, who is your father, and then delineating all possible answers to that question, from which the user can choose the most appropriate. This illustrates just one way we could get a case-specific fact into the knowledge base to help answer a query. Next, let's move on to the inference engine. Here we can see the inference engine highlighted within our expert system schematic. The inference engine obviously plays a central role in how an expert system works. Notice that the inference engine interacts with the knowledge base as well as the user interface. The inference engine is also known as a rule interpreter. It's basically the thinking part or the brain of the system. It controls how the if-then rules are applied to the facts. It allows for the acquisition of further information from the user by prompting the user for further input via a natural language interface, or perhaps by questions. And it can be used to come up with some hypothesis or solution, refine a hypothesis or solution, or resolve conflict between some currently competing hypotheses or solutions. Ultimately, the inference engine is responsible for linking rules with facts to generate new facts, where new facts represent conclusions about the state of the domain given the observations. Since we're focusing on rule-based expert systems, the inference engine is almost always going to be applying forwards or backwards chaining as the inference strategy. Recall from our lecture on rules that generally one of two specific control regimes are employed. One is the forward chaining approach, that's data-driven, and the other is backwards chaining, which is goal-oriented. Here's a table that summarizes some of the major differences between forward and backwards chaining. Understanding how both strategies work is an important element of rule-based machine learning. Recall that forward chaining starts with facts in the knowledge base. Then, inference rules are applied by matching the facts to the if part of rules in the knowledge base. This results in new facts being added to the knowledge base. Here, rules are run automatically when forward chaining is activated in order to assert new facts. The end result can be the assertion of many facts, including a particular fact that we're interested in. Differently, with backwards chaining, we start with a user-entered goal to be proven. Inference rules are then applied by matching the goal to the then part of the rules in the knowledge base. This results in sub-goals being identified that still need to be proved. This strategy continues to work backwards to the facts until we can hopefully prove the query. Now we're going to take a closer look at the components of the inference engine itself. Typically, the inference engine follows what we call a match-resolve-act cycle, although it's also referred to as a recognize-act cycle. This cycle describes the execution of rules by an inference engine. Here is an illustration of that cycle. It includes pattern matching, followed by conflict resolution, and finally consequent activation. The steps of what to do next are stored on an agenda, and depending on the type of inference we're doing, the inference engine might output new, case-specific facts that get added to the knowledge base. Recall from our rule lecture that we briefly discussed the idea of rule matching, which we'll refer to here as pattern matching. This is the first part of our match-resolve-act cycle. Matching determines the applicable knowledge in the given situation. This is the search part of the system. Rules become activated or triggered based on the type of inference or chaining being used. Forward chaining matches rule antecedents to the fact base, and backwards chaining matches rule consequence to the fact base and the rule base. Of note, the matching of many rules against many facts in the knowledge base can be computationally expensive. And also, matched rules are added to the agenda, where the agenda is a prioritized list of rules created by the inference engine. An important part of this matching process is the concept of variable binding. This is similar to binding from logic. Here, variables and rules acquire values during the matching process. Of note, both antecedents and consequence may contain variables. For now, we're going to assume that the syntax of variables will look like this example of a $x. Also of note, this is how the Pike expert system programming language syntax works, as just one example. Again, let's go back to our earlier example rules and facts, where we have if son of variable son, variable father, then father of variable father, variable son. And also let's say that these facts already exist in our knowledge base. Let's also assume that we're doing forwards chaining, which will look at any facts that match any of the ifs in our rule base. And in this case, we have son of Steve Joe matches if son of variable son, variable father. In order to make this fact properly match, this part of the rule needs to bind some variables. Thus the value Steve gets bound to variable son, and Joe gets bound to variable father. Now, when the consequent of this rule is activated, the variables in the consequent of the rule will also accept these bound variable values, meaning that we can add a new fact to our knowledge base. Specifically, father of Joe Steve, or in natural language, Joe is Steve's father. And because this is a new temporary fact, it gets added to our case-specific facts, otherwise known as our working memory. Once a variable is bound, that variable is replaced by its binding, wherever it appears in the same or subsequently processed patterns. Whenever the variables in a pattern are replaced by their bindings, the pattern is said to be instantiated, just like from the field of logic. In forward chaining, these bindings typically persist as new facts added to that working memory. However, in backwards chaining, these bindings can be temporary, as we're going about testing different hypotheses and trying to prove, through backwards chaining, a chain of truth values. The next part of the inference engine is conflict resolution. The previous step of matching can often yield more than one applicable or matching rule that are put on the agenda. So then the question is, which one do we look at first? Or do we only want to look at one of the matching rules? For example, maybe we only want one medication to be prescribed, even though multiple medications would be appropriate. Assuming that we only want one action to fire, these matching rule instances are said to be in conflict. So now we have to use some kind of conflict resolution to pick just one for firing. In this case, we'll assume we're still using forward chaining. One way to achieve this is to select the rule with the highest priority from the agenda. There are different ways to assign priority, as well as different conflict resolution strategies. Let's look at some different conflict resolution strategies. The first is order, or the source file ordering. Basically, this just means to pick the first rule that matches in the rule base based on how the rules are actually ordered in the file. However, this tends not to be ideal for very large rule sets, because now you have to worry about how all the rules are ordered in the file. Then there's specificity. Here we would pick the most specific rule. By more specific, we mean that if the conditions of one rule are a subset of that of a second rule, we choose the second rule. For example, if we have the rule if A and B then C versus if A then C, we'd pick the first rule because it's more specific. Another conflict resolution strategy is to go based on lexical order or alphabetical or dictionary order. For many problems, this is somewhat arbitrary, but it could be useful in some domains. Another way to go about conflict resolution is to assign importance to rules. This is also known as salience. Here, we want to pick the rule with the highest priority. Thus, rules have to be defined along with some kind of priority score. This is often discouraged as it can be very hard to set up precisely in large rule bases. You could also employ meta-rules to serve as tiebreakers in conflict situations. Here's an example of using importance for conflict resolution, where we have two rules: if patient has pain, then prescribe painkillers, where this rule has a priority of 10, versus if patient has chest pain, then treat for heart disease, which comes with a priority of 100. If both of these rules' conditions were satisfied, then the second rule would actually be fired, since it has a higher priority. Yet another conflict resolution strategy is that of recency. In this case, we want to pick the rule that was most recently added or modified, or that has antecedents most recently added or modified. The downside here, of course, is that you're going to have to require time tags in your implementation. And the last conflict resolution strategy we'll mention is refactoriness. This approach simply doesn't allow the same binding instance of a rule to be fired again. The last part of our inference engine that we're going to look at is the consequent activation. So now, once a rule on the agenda is selected, consequent activation is basically where we activate, fire, or trigger the rule. If we're doing forward chaining, we're executing the consequent of an applicable rule, and this results in a new fact being added to our case-specific facts. Once this is done, we can remove the rule from the agenda, since we don't have to deal with it any further. And the entire cycle of the inference engine ends when no more rules are in the agenda, or when there's some explicit stop command that's given to the system. Now let's take a stepwise look at how both forwards and backwards chaining works in the context of rule-based systems. When it comes to forward chaining, we're going to repeat the following: apply all rules to the current facts, and each rule firing may add new facts. Do this until no new facts can be added. Here's a simple illustration. We have a fact 1 here at the top. and we have a set of rules in our knowledge base indicated by the bracket. Fact 1 satisfies our first rule, which creates a new fact, fact 2, that's added to our knowledge base. This new fact then allows our next rule to be triggered, adding fact 3. Fact 3 allows fact 4 to be triggered. Fact 4 allows fact 5 to be triggered, and perhaps fact 5 is our goal, or some kind of decision or action that's going to now take place. Now let's walk through a slightly more complex example of forward chaining inference. Let's say that we start with this fact base, where A, B, C, D, and E are all facts, which could have been hard-coded into the system, or they could have been provided by the user. So now we take a look at our first fact, A, and see if it activates any of the rules. In this case, it does. A activates or triggers X, so X gets added to our temporary fact base. We then see if B can trigger any rules, but as you can see here, it doesn't trigger anything on its own. We then look at C, and in this case, C does trigger L, so at this point, L gets added to our fact base. This ends the first cycle of our forward chaining approach. You can think of a cycle as trying to add as many things as possible based on our starting set of facts. So at the end of this cycle, we have all of our original facts, but now we also have X and L as facts. So now we move on to the next cycle. Here we check our knowledge base again to see if any new rules can be triggered. In this case, we now know X, B, and E thanks to X having been added in the last round. So at this point, Y gets triggered and added to our fact base. In our third cycle, we now have A, B, C, D, E, X, L, and Y as facts. And at this point, we can now trigger the Y and D rule, which lets us put Z in our fact base. At this point, Z might be returned to the user as either the goal we were trying to prove, or maybe we're looking for some kind of recommendation and Z was provided back to the user. Notice that we didn't use all rules in our knowledge base. In this case, we never had the fact M, so this rule couldn't be triggered. We can illustrate this process of forward chaining via what we call an inference chain. So in this example, we assume A, B, and E are facts, and we have the following rules. Here, A, B, and E are facts in the chain, and we can see how one fact leads to the addition of a new fact. So for example, Rule 3 says if A is true, then X is true. So now we have A, X, B, and E. To show that Y is true, we need to show that X, B, and E are true. These allow us to add Y as a fact. And now all we need at this point is to get D to show that Z is also true. Now let's walk through similar examples for backwards chaining. It will repeat the following steps. First, see if the consequent is already in the fact base. In this example, goal 5 is the consequent that we're looking for, so we check to see if it's already in the fact base or not. If it's not, we're going to find rules that have that goal 5 target goal as their consequent. So in this case, this rule includes goal 5 in its consequent. So we'll try to prove the antecedents of that rule. In particular, we need to prove goal 4 to determine the truthfulness of goal 5. Of note, any of these rules that have a matching consequent will stack. In other words, its antecedent becomes the new target consequent or a new subgoal. So now we have to find a rule with this subgoal, goal 4, which we find here. Goal 4 is part of its consequent, or we could also see if goal 4 was already in the fact base. We basically repeat this process until a connected set of subgoals are satisfied by facts that are in either the knowledge base or the fact base. So in this example, you can see the backwards chaining proceeding backwards until we find this rule where goal 1 happens to be in our fact base. And this allows the truthfulness to propagate through this chain back to the original target goal, which was goal 5 here in this example. Of course, it can also happen that there is no connected set of subgoals that can be satisfied by the facts, in which case we'd fail to prove our goal. Now we'll go through a slightly more complicated walkthrough using backwards chaining. In this case, the goal we're trying to prove is Z. Here's our rule base, and here's our fact base. Again, these facts could be either provided up front by the user, or they could be hard-coded facts in the knowledge base. Starting from Z, we find a rule in our knowledge base that has z as its consequent. And here we see one. If y and d, then z. So at this point, we know that to prove z, we also need to prove y, and then we need to prove d. We'll start with y. So now our goal is to check if y is already in our fact base, which it's not. And since it's not, we're going to look for a rule with y as its consequent. So now this rule is something we need to prove also. Let's continue down this path to see if we can prove y. To prove y, we need to prove x, b, and e. Notably, b and e are already in our fact base, so the only thing left to prove here is x. So now we find a rule that has x in its consequent. If a, then x. Since a is a known fact, we can now add x to our fact base. At this point, our fact base includes all of the conditions of the rule if x and b and e, then y. So now we can add y to our fact base. Going back to the first rule we were trying to prove, if y and d, then z, now we know that both y and d are true, or satisfied, so we've proven our goal of z. In this case, we have a successful example of backwards chaining proving the query. When you have a query fail, you can have the interpretation of failure as negation. In other words, failure to prove the query could be used to suggest that it's not true. However, failing to prove a query could also just mean that the database was incomplete or inadequately maintained, so that's something to keep in mind. Under some circumstances, there's a possibility of infinite looping when attempting to retrieve some missing information. In these cases, it's necessary to apply termination criteria that will explicitly detect this and allow the system to fail gracefully. So be cautious that when you're building an expert system, that you avoid creating situations where the occurrence of an infinite loop is possible. Some expert systems can apply both forwards and backwards chaining simultaneously. This is referred to as mixed chaining or hybrid chaining. The strategy here is for the system to chain first in one direction and then switch to the other direction, so that the diagnosis is found with maximum efficiency. For example, in asking the minimal number of questions to prove a goal. This kind of systems behavior is often perceived as being more human. When it comes to the efficiency of an inference engine, we might ask, how do we reduce the cost of the matching process? One way is to use Markov algorithms. Here, rules with higher priorities are applied first, and this allows more efficient execution of production systems. However, this kind of approach is still not efficient enough for expert systems with large sets of rules. Another approach to reducing cost of matching is to save intermediate match information. The idea here is so that matching doesn't take place again and again and again when it doesn't need to. Here we share intermediate match information between rules and recompute intermediate information for changes. But this requires extra memory for intermediate match information. But in the long run, this scales better to larger rule sets. Another efficiency approach is to recompute matches for rules affected by change. This has been referred to as the treat algorithm, which is a variant of the ret algorithm. Here we check changes against rules in the conflict set. This takes up less memory than the read algorithm, but it doesn't scale as well to large rule sets. In general, we can also make expert systems more efficient by making extensive use of hashing or the mapping between memory and tests or rules. In our last section of this lecture, we'll briefly review other components of a rule-based expert system. Here again is our expert system schematic. We're going to go into a little bit more depth on things like the knowledge base editor, the explanation system, and the user interface, all indicated here by green arrows. First, the user interface is a means of interaction between the user seeking a solution and the expert system. The interface allows us to edit facts or rules, query the system, answer questions, and be presented with solutions and explanations. The user interface is directly or indirectly connected to all parts of the expert system. And the user interface itself could be simple and just provide questions or answers, or it could be more sophisticated and include some sort of menu-driven graphical user interface or GUI. And even other systems could accommodate a natural language processing approach. This can make the system easier to use for people who might be well acquainted with the application area, but not necessarily AI systems or computer science in general. Next, we have the knowledge base editor. As previously mentioned, this is also known as the knowledge acquisition facility. It provides an automatic way for the user to enter knowledge into the system and bypass the need for explicit coding experience. Ultimately, it facilitates the integration of new knowledge and the editing of existing knowledge in the knowledge base. And lastly, the explanation system is also known as the justifier. This explains the reasoning of an expert system to the user. For example, how is a particular conclusion reached by means of a reasoning chain? This can highlight what rules were fired and what facts were detected along the way. They can also be used to answer why was another conclusion not reached, or why a specific fact is needed if requested by the system from the user. And it can also be used to answer why a fact was not used, or maybe why it wasn't a part of an inference chain. An explanation system is obviously important for situations like where a physician has to understand the reasoning of a recommendation. The explanation system component of an expert system is a major advantage over other kinds of representations, including neural network-based systems. So, despite the notable success of neural network systems, in many current works, expert systems are likely to remain in use for a long time as the AI technique of choice for safety-critical applications, such as medical diagnosis, or in situations where there might be legal concerns, such as where a verbal defense of a decision must be available on request. To summarize this lecture, rule-based expert systems are the most popular and traditional strategies for expert system development and application. The knowledge base of these systems are typically made up of rules, general facts, and questions that are meant to be answered by the user. The inference engine of these systems employs a match, resolve, act cycle for executing rules to derive or acquire more knowledge or draw conclusions. These systems most commonly utilize forward chaining for reasoning, but also can employ backwards chaining or even both. And rule-based expert systems can serve as more flexible and usable tools if they also incorporate a user interface, a knowledge base editor, and/or an explanation system. I'm Ryan Urbanowitz, and thank you for joining me for this lecture. Stay skeptical, curious, and creative.